Hi guys,
welcome back. So we're going to recap a little bit on what we have learned last week, which is the energetics of a solution, right? So what happens is now we're going to get an ionic solid and we're going to throw it into water and we're going to see what's the energy changes, right? So the first thing we'll look at is actually the enthalpy change of solution. The definition once again is to look at one mole of solute. You're going to dissolve it in a solvent, which typically is going to be water, and you're going to form an infinitely dilute solution under the standard conditions here, right? So if I were to use NaCl as an example, so we're going to take the solid solute, okay, NaCl. Tell me how you're going to write the equation.
So you're going to dissolve in water. So usually we'll just write plus AQ to represent it dissolving in water, right? So when sodium chloride is a soluble salt, it dissolves in water, right? It will become its ions, Na plus A equals, and Cl minus A equals.
That's right. So I'm going to use a diagram to represent the dissolution process, right? So the ionic solid is over here, and you dissolve it, and it's going to give you your ions, and these ions are all surrounded by water, which is a process of dissolution, right? Unfortunately, this whole process doesn't just happen instantaneously. You can broadly divide this into a two-step process. So the first step is actually to go and break all the ionic bonds inside the solid so that we're going to get their separated ions, and after which I'm going to throw them into water. In the context, we're going to surround them with water molecules, right? So each of these steps is associated with an energy change. Can you run us through the first one, Mr. Yap?
So the first one involves breaking the ionic bonds and separating the ions, right? So that has to do with lattice energy. So the definition of lattice energy is on the screen. Essentially, is the heat evolved when one mole of an ionic solid is formed from its constituent gaseous ions, right? Under standard conditions. So if you were to write an equation for sodium chloride, right, it will be Na plus gas plus Cl minus gas, producing the NaCl solid.
That's right.
Right now, so the magnitude of the lattice energy is now dependent on two factors. It's dependent on the product of charges. It's also inversely related to the sum of ionic radius, right? As seen on the equation.
Right.
Okay. So, but if you realize, lattice energy is about forming an ionic solid, but the dissolution process is actually the opposite. I'm breaking up the ionic solid into gaseous ions. So this process will actually be negative Le. Right? Now, Mr. Leong, after I break up the gaseous ions, what do I need to do next?
So I need to surround them with water molecules, right? This process is known as hydration, which will lead me to the next enthalpy change, which is the enthalpy change of hydration. So just to remind you again, what's the definition? We are looking out for a specific gaseous ion now, not both of them, either just a cation or an anion, and we're going to throw them in water. So we dissolve them in a large amount of water, once again, always under standard conditions. Now I'm going to use Na plus as an example. So by definition, we are going to dissolve one more of sodium plus ions, right? And of course, you say throw in water, you must put it in AQ, right? And of course, you're going to end up with the hydrated version, which we call this the aqueous ions. Now, for hydration, it is going to be dependent on this thing called the charge density of the ion. And we learned it from chemical bonding, that it depends on this very important formula, which is charge over the size, right? Now, coming back to the diagram over here, so these two would simply just be the hydration of the respective ions, right? So for the sodium, it's going to get its own hydration. Its chloride is going to get its own hydration as well. Okay, so essentially when I look at this whole diagram itself, right, I have accidentally formed an energy cycle. So you can see that the center of my cycle is in the middle, and therefore we're going to apply Hess's law, and that is why we end up with this equation over here. Okay. Unfortunately, even though I'm a man of shortcuts, there's no shortcut for this particular formula.
If you guys have any suggestions, please tell us in class. We'll be more than happy to feature you next time.
So we're going to cover new content now. Okay, we're going to look at this thing called the Born-Haber cycle, right? Now, Born-Haber cycle usually applies only for ionic substances, right? And the whole idea over here is to connect the enthalpy change of formation of an ionic substance with its lattice energy, right? So let's start off with the first one, formation. Mr. Yap, throw you a challenge. Give me the equation again.
Okay, so formation is to form one more of a compound in a specified state from its constituent element. So it's made out of sodium, right? So sodium in the solid state, standard conditions.
As well as?
Chlorine. Gas, Cl2.
Cl2, right? Okay.
Right, and to balance it, now bear in mind you are producing one more of a compound, so the coefficient in front of a compound must be 1, and therefore you have to write a half in front of the Cl2.
That's right. So this is called the enthalpy change of formation. Right. Now I'm going to link it, or rather I'm going to try to write out the equation for lattice energy now. So once again, run us through it.
Oh, me again? Okay.
Of course.
So lattice energy is to form one more of an ionic solid from its constituent gaseous ions. So NaCl is made of Na plus and Cl minus, right? So it's just Na plus and Cl minus. Both of them are in the gaseous state.
That's right. Now, if I look at this, right, you say that I want to link them together, right? It's not a complete cycle yet.
Something is missing on the left, right?
That's right. So we want to try to link it up together. Can you tell us how to do that?
Oh, Looks very complicated. I think they involve more than one step, right?
That's right. So the sodium solid, you're trying to turn it into the ions in the gaseous state. The chlorine gas, you're also trying to turning it into your chloride ions. So this one over here is going to involve multiple steps. And before we introduce the complete cycle, I think we need to look at certain definitions, right? Okay.
Oh, definitions again.
Oh, hi, Mr. Yap. What shenanigans are you up to this time?
Oh, Mr. Leong, I'm trying to atomize. Can't you see that?
But you're already so short, why must you atomize further?
Oh my god. Mr. Leong, do you hear something?
No, what?
It's my heart breaking.
Okay, moving on.
Hey, can you pull me up, please?
You have a backbone, is it? Oh my gosh.
Okay, thank you.
Okay, so let's take a look at the standard enthalpy change of atomization, right? So this was one of those that we need to go and complete our Born-Haber cycle, right? Okay, so let's look at the definition. We are going to take a look at one mole of gaseous atoms being formed again, right? And it must come from its elements this time under standard conditions. So we illustrate this with a few examples. The first of which is going to be a sodium. So remember, based on definition, we're trying to form one mole of gaseous atom. So we must start off with always the product, and we want to take a look at what is the usual element. So in this case, what will it be?
Right. So sodium under standard condition of 298 Kelvin and 1 bar, it must be a sodium metal, right? So it's solid state.
That's right. Okay. Now, how about bromine then? So I'm trying to form one mole of gaseous bromine. Where must it come from?
From a bromine molecule, but under standard condition of 298 Kelvin 1 bar. I hope you guys remember your group 17 chemistry. Bromine is a liquid at room temperature and pressure.
So bear in mind, this is a liquid, okay? And how about for phosphorus? So once again, I'm trying to form one mole of gaseous phosphorus atoms.
But phosphorus is a bit tricky. You guys might not have seen this before. Phosphorus exists as a tetratomic molecule at standard conditions, or P4. So just take note, you have to balance it with a quarter in front.
That's great. Okay, now what about, let me show you a challenge, okay? What about if I ask you for neon gas? So let's write down one more. Yes, Neg, right? One mole of neon gas, who should it be formed from?
Neon. So neon is also a gas at room temperature and pressure, right?
Right. And more importantly, this is
a monoatomic gas, right?
Monoatomic.
Because it's a noble gas.
That's right.
So it's essentially the same thing, right? Neg become Neg.
So what do you expect the enthalpy change to be?
0.
Okay, so therefore in this case, if you ever have a monoatomic element, the enthalpy change of atomization for that particular element is going to be 0, right? So this is usually the case for noble gases because they are the ones that are usually existing as monoatomic. Okay. One important thing that I noticed over here, right, Mr. Yap, is that all these enthalpy changes of atomization are all positive. Can you shed some light why this is so?
Because our enthalpy change of atomization is an endothermic process because it involves breaking of bonds, could either be metallic or covalent bonds in nature. So that's why it's always a positive value.
Very insightful. Now, the second enthalpy change we're going to look at for Born-Haber cycle is going to be the ionization energy. So this one shouldn't come as a surprise to you because you have learned this in atomic structure, right? But just to recap, if you are looking at the first ionization energy, we are looking out for the number of the energy absorbed when you remove one mole of electrons from one mole of gaseous atoms to form a singly charged gaseous cations, right? So a very mouthful, but we'll use an example. If I look at calcium, we start off with a calcium atom, and you want to remove one electron. So therefore, you're going to end up with a cation that's singly charged. And if I look at the ionization energy, right, it is actually an endothermic process. Why is that so, Mr. Yap?
Right, so because you are removing the electron from the atom, so you must free the electron from the whole of the nucleus. You need to overcome some electrostatic attraction. Energy is needed, endothermic, that's why.
That's right. So what happens if I decide to look at the second ionization energy?
Okay, always asking the insightful questions. So for the second ionization energy is the energy needed to remove one mole of electrons from one mole of a singly charged gaseous cation to form one mole of a doubly charged gaseous cation. So in terms of the equation, it's whatever Mr. Leong is writing on the screen now.
That's right.
All right, Mr. Leong, so you asked me what is second IE, right? Can I ask you back what is third IE?
Sure, but I think I should pose this question to the students, right? So you will answer it in class.
What about fourth IE?
You will answer it in class.
Fifth IE?
You will also answer it in class.
All Mr. Leong students, please prepare the answers for all these. We'll ask you in class, okay?
Sure.
Alright, so the next thing we're going to look at is electron affinity. Now, electron affinity essentially is the opposite of ionization. Ionization removes the electron. Electron affinity puts the electron back in. So first electron affinity is the energy released when one mole of electron is added to a mole of gaseous atom to form a mole of singly charged gaseous anions. Alright, now if you were to look at the example below, right, so oxygen atom taking in one mole of electron to form O minus. Right, Now, Mr. Leong, you will notice that the first electron affinity is exothermic in nature.
That's right.
Could you share some light?
Okay, sure. So it's exothermic. The reason why is because we are pushing electrons into the atom, right?
Yep.
So in order for the atom to hold the new electron in place, it definitely must form some electrostatic attraction between the nucleus and this incoming electron, right? So as a result, this feels like it's a bond-forming process, and that is why this is an exothermic reaction.
All right, that's good. Now, in terms of the second electron affinity, so if you look at O minus as a sample, so you're going to put in another electron into the O minus to make it O2 minus, but you will realize that the second electron affinity is positive in nature. Now, Mr. Leong, why do you think is this so?
I must shed some light now again, right? Okay, so obviously, you might think that the second EA might have the same idea as the first because you're trying to form electrostatic attraction, right? But the problem over here is that you notice that there is actually two negatively charged species coming very close together. And what do you think will happen?
Negative, negative, repel?
Repel. So therefore, if you insist on this reaction happening, right, you say that I need to supply some energy to push them close together before they can collide and they can react.
So you need to force them together, you need to invest energy into it, therefore EA2 would be endothermic in nature.
That's right.
So in fact, EA2, EA3, EA4, and so on will always be endothermic. So only first EA is usually exothermic for non-metals.
That's nice. So after learning all these definitions, right,
we can many definitions.
Okay, so we can finally connect our Born-Haber cycle, right? So I think our job just now was to try and connect all these elements into their gaseous ions. Yeah. So can you now help me to connect the dots?
Help you? Sure. So for sodium solid, you first need to make it into a sodium gaseous atom, so NaG.
Okay.
Then after you make it into NaG, you can just remove one electron from it to get Na+. So that, right? So that's that. Now in terms of the non-metal, you need to make once again it into an atom, chlorine atom. Then the electron lost by sodium would be forced into the chlorine atom to make it in the Cl-.
Okay. So in terms of the energy changes wise, you tell me that the sodium become the gaseous atom. What kind of enthalpy change am I looking at here?
Enthalpy change of atomization.
That's right. Atomization of your sodium metal, right? Yep. How about turning it into the ions?
First IE.
First IE. That's right, because you're removing electrons. Now, conversely, for the non-metal, the chlorine diatomic molecule become chloride atom.
Yes. Atomization as well.
Atomization again, right? And how about from chlorine into the ion?
It's the opposite of taking out electron, so it's EA, putting in the electron.
That's right. So there you have it. This is the complete Born-Haber cycle, right? But this is not all, because sometimes instead of doing the cycle, they might choose to do the energy level diagram, right? So we're going to run you through this using the acronym over here, which is called FAIL, F-A-I-L.
Learn already will fail chemistry now.
Won't if you learn already, then you won't fail lah.
Never learn, then will fail, is it?
Yes, correct. So we're going to take a look at what does the FAIL actually represent. Now, first of which, the F stands for formation. Okay, so we're going to start off our energy cycle with the zero energy level, which this always represents the elemental form. Right. So I assume that your ionic substance is given by Mx over here. M is the metal and X is the non-metal, which I'm going to assume that it's going to exist as a diatomic molecule under standard conditions. So we're going to also assume that the formation is going to be exothermic. So I'll write out the energy level first, right, for the reactants going downwards towards the products. That is your F. Okay. Can you run me through A then, Mr. Yap?
Right, so A stands for atomization. Usually we will just do it atomization of the metal first, followed by the non-metal. So let's atomize the M first.
Okay, so
MS, we're going to change to Mg. Right?
So that's what you see over here, right?
Yep. Okay, then after you atomize the metal, you atomize the non-metal. Right? Do it systematically.
Okay.
Right? So after you represent it on the screen, right, half X2 become Xg. Right? Now after you atomize the metal and non-metal, the next one is I, right? Ionization. So you need to make it into ions. So let's make, we remove the electron from the metal first. So that's first IE. Now the electron is produced. Please remember to write it.
Sure.
Right? The electron produced lost by the metal will now be added into the non-metal. So the non-metal will take in the electron, that's first EA. Right? Remember EA is an exothermic process, so please remember to point it down. So now what you have left with is the gaseous ions, right? So what's the last arrow, Mr. Leong?
It's going to be called lattice energy, right? So that is going to be the L of the FAIL, right? Now, if I look at this over here, right, there's something a little bit different, okay, of which we're going to look at this atomization of the non-metal, right? Because normally they don't usually give you this inside your question. What do they normally give you?
Usually they don't give you anything. You're expected to know where to find it from.
Okay, so turns out we have to use the idea of
bond energy.
Bond energy, which can be found inside your data booklet, right? But one problem about the bond energy is this. Let's write out the equation and see what's the problem.
Sure.
Okay, can you help me out with that?
Yeah, so the definition of bond energy is the average energy needed to break 1 mole of a gaseous covalent bond. Right, so the number in front of the reactant must be 1 because it's 1 mole of a bond in the reactant.
That's right.
Right, but if you realize the equation representing the atomization of X, right, is not the same as the equation representing the bond energy, right? What's the difference, Mr. Lau?
So this one only requires you to have one X atom, but for bond energy, it's actually going to give me 2, right? So what's the consequence then?
You need to halve it essentially.
That's right. So I need to halve everything. So half here, this one becomes 1, and this one will become a half over here, right? So that's exactly matching up to this equation, which means that if I try to look at the atomization of X, it is essentially the same thing as half of the bond energy for your X2. Okay. Right. Now, drawing all this is good. At the end of the day, I still need to use an equation to connect all these enthalpy changes together, right? So what's next?
Right, your favorite. Clockwise equals to anti-clockwise, which is Hess's law.
Right. So I think over here it's pretty straightforward. You tell me that the center of a clock is here, right? And we're going to look at all the clockwise arrows, which I hope is not too hard. It's going to be looking like this. So you're going to add up all these enthalpy changes that I've highlighted for you. And this is going to be equated to the only anti-clockwise arrow that you see over here. That is written in green. So just equate these two equations together and probably you'll be able to find out the unknown, which is usually what the question wanted. So with that, that's it for Born-Haber energy level diagram. So we're going to try more questions to deepen our understanding.
Okay.
See you in class.
Making sense beyond simple solutions.